Welcome to this podcast series. My name is Johnny Lee from the Department of Statistics and Actuarial Science at the University of Waterloo. Well, this podcast is about multi-population mortality modeling. So before I go into the details, let me explain a little bit why do we need multi-population mortality models. Well, multi-population mortality models plays a crucial role in longevity risk transfers. Nowadays, pension plans may transfer their longevity risk exposures by trading derivatives that are linked to human mortality rates. Well, if they mitigate longevity risk by using such an option, they will be exposed to population-basis risk because the population that is linked to the security may not be identical to the population that is associated with the pensioners because the population that is linked to the security may not be the same as the population that is associated with the pension portfolio. Multi-population mortality models are also useful in pricing and risk management for securities that associate with multiple populations. For example, in 2011, Swiss Re Insurance issued a bond called the Quartus Deal. The payoff of this bond is linked to the divergence between the survival rates of England and Wales population and the US population. There are also many traditional actuarial applications. For example, we can use multi-population mortality models to capture the mortality of both genders simultaneously. And we may also use a multi-population mortality model to add credibility to projections for smaller populations. In my own opinion, the most influential paper in the topic of multi-population mortality modeling is the paper that was written by Non Lee and Ronald Lee in 2005. In that paper, the authors proposed a new concept called coherence. Now, under the coherence hypothesis, the projected future mortality rates of two or more related populations should not diverge over the long run. For example, let me consider the augmented common factor model that was proposed by the same authors. Well, in that model, the mean time trend that is shared by all populations is captured by a random walk with drift. But then the population-specific time trends are captured by autoregression. Autoregressive processes. So in this way, the gap between the mean time trend and the population-specific time trends will revert to a long-term mean over time. And the hypothesis of coherence has been used widely in subsequent studies of multi-population mortality modeling, include the paper authored by this group of authors. The rationale behind the coherence hypothesis is that mortality projections that diverge indefinitely over time do not seem to be biologically reasonable. The coherence hypothesis is also supported by some empirical observations. For example, in the paper by Wilson in 2001, the distributions of global population by life expectancy over 3 different periods of time are observed and compared, and it is found that the dispersions of these distributions reduce over time. And a similar study conducted by White in 2002 also led to the same conclusion. Nevertheless, there exists some evidence against the coherence hypothesis. For example, in the paper by Opan and Wapao in 2002, they studied the notion of best practice life expectancy, which is shown in the straight line, the upward sloping straight line on this diagram. Now, on this slide, we also show the life expectancy over time for 5 different national populations. We do observe that for some populations, such as Japan and Chile, their life expectancies converge very quickly to the best practice level. But then, For some populations, such as the United States, over the past 2 decades, their life expectancies are actually moving away from the best practice level. In addition, some researchers also found that individuals with high incomes experience faster mortality improvement. So these findings has led us to 3 questions. Number 1, is the coherence hypothesis always true, always acceptable? Number 2, if neither the non-coherence hypothesis nor the full coherence hypothesis is acceptable, do we have a third option? Number 3, if we assume the coherence hypothesis in actuarial evaluations, but then if the full coherence hypothesis turns out to be incorrect, what will the financial consequences be? So in this video, I am going to look into these 3 questions. There are 3 objectives. First of all, I'm going to introduce a new concept called semi-coherence. Under semi-coherence, the mortality trajectories of two related populations are permitted to diverge, as long as the divergence does not exceed a specific tolerance corridor, beyond which mean reversion will come into effect. And then, in the second objective, I'm going to explain how we may use a vector, threshold, autoregressive, or vector process to implement the concept of semi-coherence. And finally, I'm going to address the impact of hypothesis risk, i.e. the risk that the full coherence hypothesis turns out to be incorrect. In this video, I'm going to focus on the first objective, and in the next video, I'm going to go through the second and the third objectives. So let me begin by describing 3 different forms of coherence. First of all, non-coherence. Well, if we arbitrarily combine 2 single population models, the resulting forecast is generally non-coherent. As an example, let me consider a combination of 2 completely unrelated single population Lee-Carter models. Well, in this model, we model the log of the central death rate arm at age x in year t by using a combination of 3 parameters, alpha, beta, and kappa. Alpha and beta are age-related, and kappa is related to time. And to capture the evolution of mortality over time, kappa is modeled by a random walk with drift. What I'm going to do next is to estimate this model to the populations of England and Wales and the United States completely independently, so that these 2 populations will have different alpha, beta, kappa parameters and also 2 different random walk processes. So on this slide, I show the projection results on the basis of the non-coherent approach. This slide shows the projected central death rates in log scale for age 55. The dots represent the historical values, while the solid lines represent the forecast produced by the non-coherence model. Now we see that the forecast for the 2 populations diverge indefinitely because there is absolutely nothing to tie them together. And as I mentioned earlier, such a forecast is deemed biologically unreasonable. Now, let me move on to the other extreme, full coherence. By full coherence, we mean that mean reversion always exists to prevent the expected trajectories of the log central death rates of the 2 populations from diverging indefinitely. So there is always a piece of string that ties the 2 populations together. As an example, let me consider the 2 population Lee-Carter model considered by Andrew Carnes and his co-authors in 2011. So as before, this model described the log central death rate at age x and in year t as a combination of 3 parameters. Now this particular model assumes that population 1 is the dominant population, population 1 is the driving force, and the other population, the non-dominant population, is the follower. So for the dominant population, the evolution of copper is, as before, modeled by a random walk with drift. The most striking difference between this and the non-coherent approach is that the gap between copper 1 and copper 2 is captured by a first-order autoregressive process, so that the difference between copper 1 and copper 2 will revert to a long-term mean over time, and in this way, full coherence is achieved. So I estimated the full coherence model to exactly the same data set, and here I show the projection result. As before, I showed the log central death rate at age 55. The dots represent the historical values, and the solid lines represent the forecast produced by the fully coherent model. Alright, so in my estimation, I assume that the population for England and Wales is the dominant population. So the projection for England and Wales is similar to what we saw in the previous picture. But in contrast to the fully coherent approach, there is always a string that ties the two populations together. So as a result, we observe that the forecast for the US population starts to converge to the long-term equilibrium at the forecast origin, and the conversion is pretty quick and is completed in around 10 to 15 years. But because of this, we also see some anti-intuitive phenomena in this forecast. For example, there is a sharp turn at the forecast origin, which does not seem to be easy to explain. The limitations of the full coherence approach can also be seen in this picture. Now in this picture, I show the estimates of copper 1 and copper 2 in the entire sample period. We observe that over some periods of time, the trend for one population reduces much faster than the other population. As an example, let us consider the period from 1990 to 2010. Over this period, the corpus for England and Wales reduced much quicker than that for the United States population. So, from this picture, we can infer that the full coherence hypothesis may be too stringent, and on the next slide, I'm going to introduce a compromise: semi-coherence. Well, semi-coherence is less restrictive than full coherence, but it still includes some sort of mean reversion. In more detail, under the semi-coherence hypothesis, a tolerance corridor is imposed on the mortality differential between two populations. If the tolerance corridor is not exceeded, then the expected mortality trajectories of the two populations may diverge. Otherwise, the system will switch to an order state in which the expected paces of mortality reduction will be adjusted so that the mortality differential in absolute value is expected to shrink over time. I think it will be easier to understand the hypothesis of semi-coherence by using this picture. Now on this picture, the vertical axis represents the mortality differential, the horizontal axis represents time, and the dotted red lines represents the tolerance corridor. So within the tolerance corridor, the mortality differential may diverge, but once the tolerance corridor is exceeded, mean reversion will kick in so that the mortality differential will be pulled towards back to the tolerance corridor. Given how we define the hypothesis of semi-coherence, we can see that non-coherence and full coherence are indeed special cases of the semi-coherence hypothesis. So for non-coherence, we can see that it actually represents the extreme case when the bounds of the tolerance corridor is positive infinity and negative infinity respectively. And for full coherence, it corresponds to the special case when the tolerance corridor has a zero width. Without using any model, we can deduce just from the definition of the semi-coherent hypothesis, some properties of semi-coherent mortality forecasts. First, mean reversion does not necessarily begin at the forecast origin. Second, the expected mortality trajectories of the two populations being modeled can diverge over certain periods of time, and in this way, the projections can cover a wider range of possible mortality differentials. This property is important because otherwise we may understate population basis risk. Finally, from the definition, we can tell that mean reversion will come into effect at different time points when the tolerance corridor is exceeded. It is this intermittent mean reversion that prevents the expected mortality trajectories from diverging indefinitely. So that's the end of video 1. In the next video, I'm going to explain how we can actually implement the semi-coherent hypothesis.